Great. Okay, so hi, I'm Alvina, and I recently obtained my PhD from UCL, and I'm also a visiting researcher at NTHU. So I'm excited to be here today to talk about how we can map the magnetic universe through radio observations. So as we all know, magnetic fields are everywhere around us, yet the big questions still remained, which is where do the first magnetic fields come from? And how do they evolve with the structure formation of the universe? And the reason why it is challenging to study magnetic fields is because it is simply invisible to the human eye, which means we can only infer their presence and diagnose their properties through indirect methods. And here in the background, if you can see it, are the northern lights, and it is a beautiful evidence of the Earth's magnetic field interacting with the charged particles carried by the solar wind. So if we move on to larger scales than our sun and the Earth, such as the galaxy that we live in, the Milky Way, it is also magnetized, as well as larger scale structures like our nearby galaxies and galaxy groups. And in the last 2 days, we have heard a lot about detecting and studying galaxies in the optical and infrared, and how these can shed some light on their properties, such as their environment and how they evolve. But don't forget that galaxies are also threaded with magnetic fields, which may be weak, but still play an important role in their dynamics and evolution. So for galaxy clusters and beyond, thanks to Yenting and Kevin earlier for mentioning why they're so important, it becomes more difficult for us to see and measure the magnetic fields because they are just a lot weaker. However, it is very important to correctly infer the magnetic field properties at such large scales because they should hold some evidence of the first magnetic fields. So right now, we still don't know whether the first magnetic fields are primordial in origin, which means they are created soon after the Big Bang, or are they generated through some astrophysical processes after the first stars and the first galaxies form. But soon enough, we would have some answers, hopefully, when the world's largest radio telescope, the SKA, comes online, and is expected to carry out an all-sky survey of over 10 million rotation measures, which is many, many times of what you see here, a rotation measure map that was compiled, I think, in 2012, which only had about 1,000 plus rotation measures. So with more FRBs and with more quasars to be detected in the future, which can be used as background lighthouses, the SKA is what we call a big data project for machine learning, and it would be also able to detect the very weak magnetic field of the cosmic web. So it is crucial to infer the magnetic field properties from rotation measure correctly. And by definition, the rotation measure quantifies the amount of rotation that occurs when the polarization plane of light rotates in a magnetic field. So observationally, we can obtain the rotation measure by measuring the change in the polarization angle seen on the sky at various wavelengths. For example, the Coma cluster here, whose rotation measures of a bright polarized source behind it are derived from the slopes of best fit. And on the left, we can see that the intracluster medium is magnetized through the detection of diffuse megaparsec scale radial contours. So we have the rotation measures. Now, how do we relate it to the magnetic field strength along the line of sight? So we can do that through this widely used equation here. And this equation is actually derived from the theory of polarized radiative transfer, given that there is no absorption, no emission, no Faraday conversion, and that only thermal electrons are present. And it is often argued that the correlations in the observed rotation measure fluctuations give us some information about the length scales on which magnetic fields vary. So what this gives us is what we call the conventional approach, and it is to model the rotation measure fluctuations as a random walk process, which gives us the standard deviation of the rotation measure, and this can be used to quantify the fluctuations in the line of sight magnetic field. And most studies on large-scale magnetic fields use this expression. But the question is it really valid in all astrophysical scenarios? So to verify, what I did was I carried out Monte Carlo simulations to compute the rotation measure fluctuations, first using the conventional approach I shown earlier, and then I compare it with the results from a standard polarized radiative transfer calculations. So here I built models of various magnetic field configurations and thermal electron number densities. Then I made sure that my magnetic fields are divergence-free, and I normalized my data cubes to galaxy cluster scales. So here is a key result, one of the key results from the conventional approach. And let's do an eye test. I'm not there in person, but can you see any difference between each panel shown on the screen? So the answer is no, because all of them, it's okay. So the answer is no, and all of them actually look the same. So you're correct. And however, these are actually synthetic rotation measure maps, which I computed using completely different distributions of density and magnetic field. And in fact, what you see in the bottom row here, the magnetic fields are actually unphysical, which means I deliberately made them non-divergence free. And the key point here is that from the observed rotation measure maps alone, it is not trivial to characterize the thermal number densities and the magnetic field strengths. So not only that, we also found that the conventional approach is unable to distinguish between various distinct distributions of densities and magnetic field strengths. So what this means is that the conventional approach cannot tell the distributions of density and magnetic field strengths apart, whether they're uniform, Gaussian, fractal, or log normal. And secondly, we also noticed that the conventional method do not work for fractal and log normal density distributions. And this is actually quite a problem because log normal and fractal distributions in densities are very common in many astrophysical systems, such as the intracluster medium and molecular clouds. Furthermore, fluctuations of density and magnetic fields along the line of sight and across the sky plane can be quite different. So for instance, what I've shown here is a schematic, and what we see on the sky are two similar angles. However, each of them has a different characteristic length scale along each line of sight, A and B. So A has two characteristic length scales and B only has one. And yet, none of these length scales actually correspond to the length scale that we see on the sky. Hence, what this means is that when we take a radio picture of the sky and we derive a correlation length scale of the magnetic field, this does not necessarily directly translate to the correlation length scale of the magnetic fields as it evolves from the past to the present. So my take-home message is that please be very, very careful when you try to interpret magnetic field properties from rotation measures, and I would strongly suggest a polarized radiative transfer calculation as a more robust alternative. So that's all from me today. Please feel free to ask me any questions, and if you're interested in more details, please take a look at these two papers that we wrote. Thank you.
Thank you very much. We got some questions on Slack. The first one is about your distance between the source and the observers. In your RM model, is the distance independent or model dependent or model independent, or how do you decide the distance of the source that you are observing?
So let me go back. So when we make the models, the distance is determined by the big L here. And the question is whether it's model independent or model dependent. So the distance matters. The distance between the observer to the source matters. And how do I decide the distance of the source that you're observing? Oh, so in this case, because I'm interested in galaxy clusters, I just use a distance of about 1 megaparsec, which is the typical length scale of a cluster. And you can decide whichever distance you like to use as a researcher, depending on what kind of system you're looking at. So if you look at something smaller, you can use a smaller length scale. Yeah.
Okay. I have another question from Dari.
So in your slide of before your take-home message, what physical distance can cause signal A to have two characteristic length scales?
Oh, okay. Let me go to my backup slide. So what happens is that, in the real world, we can have different astrophysical conditions, such as what you see here. And the different A, B, C, D, E, F are just different possible astrophysical conditions. And what happens is that sometimes you can have a background source. For example, you can have an FRB, and you can be looking at it. And what's in between is ICM or the IGM. Or you can have nothing in the background. So depending on what kind of arrangements you have, whether or not you have a source at the back or in front, that can cause the different characteristic length scales. Because if you think of the object as being able to flip the angles, so if you think of the magnetic fields for example, a strong magnetic field in the FRB is able to flip the polarization angles a lot more than when you have no FRB. And that can actually change the characteristic length scale depending on how your astrophysical system looks like. Does that answer your question?
Yes, thank you. That was a great explanation.
Thank you.
Okay, do we have any more questions, comments from local or remote persons? We still have a bit more time. If no, then let's thank the speaker once again. Thank you, Alvina.